Hello, Heskett Eagles, sixth grade Eagles. This is Miss Patty.
And this is Miss Towles, and today we'll be going over the measures of the center and variability. But our objective today is going to just be understand that a data distribution can be viewed by its shape and it can be analyzed by its distribution. And our standard number is for today is going to be 6 SPA2. And also our prerequisite skills should be understand statistical questions and data collection. Previously, we talked about what was a statistical question and a non-statistical question. And then we're going to understand that graphs and tables organize data. So the next thing we're going to look at are the lessons vocabulary. Go ahead, Ms. Petty.
All right, so I'm also going to draw while we do this. We're going to talk about the word cluster. It's a group of data points that crowd near each other. So if I have a simple line plot, I have some values down there, and then I have our tick marks, our X's. We can say that the data is clustered around these values here. And if you want to give them a random number, just say 2 and 3. So my data here is clustered around 2 and 3. That makes sense, right?
And so means crowding around each other. Like when we have dances, everybody clusters in a circle and dance like that. So then we go into screwed left, where most of the data points on a graph are clustered near higher values. The tail is to the left, but most of the data is all the way, the tail is to the right, but most of the data is to the left. Actually, no, I said that backwards. I apologize. The tail is to the left, but most of the data is to the right, so therefore it's clustered to the left.
Right, because this little thing over here is the tail. Should do this and I give it green. Now, and then skewed right is just the opposite of skewed left. So we'll have some data points, and they're going to be clustered at the low values, and the tail be over on the right.
And that's why it's skewed right, because that's where the tail is.
Okay,
and
go ahead.
The metrical graphs. Those are graphs that have the same shape on either side of a middle point. So when she puts the middle here, if you put that, make that line further down the middle, each side has the same shape.
And then a peak. So we can identify a peak on our graph that we have. Very easy. It's at the top, right? It really could be in the middle. So this whole thing is our peak of the graph, just like the top of a mountain.
Exactly.
If it was a line plot, we have some points here, point there. I say a lot of points right here.
And that would be the peak of your data.
Right. The peak of the data will be this part. Right. And then our last thing is going to be outliers. So if I'm just going to do a simple line plot.
So the outlier is a data point far away from the other data points. So as Ms. Petty draws that line for you, I'm going to give you a real life one. We're inside a classroom, 6th grade. Most everybody's 11 and 12. But the teacher would be the outlier age-wise, because the teacher's age is maybe 3 to 4 times more than your age. So it's all skewed towards the right, because the number is going to be higher. So let's say the teacher's 45 and you're 12 or 11. That means 45, the teacher's age, is an outlier in the classroom.
So everybody's at least between 10 and 13. And exactly. Then teacher is going to be over there, 45. Just to make this right, we're going to put our dots, our ellipses. Now, let's say there's a break in this graph. So let us know if you have any questions about these, and we're going to erase this page. And everyone should get out their practice and problem solving now.
So now you have your example here. So we're going to study examples showing how to interpret the distribution of data in a line plot. Then we're going to solve problems 1 through 8. we're going to go through the first one with you, and then we're going to have you do the rest by yourself, and then we'll probably go through questions 1, 4, and 8 with you. So an example, it says, there are several rare insects on display at the insect exhibit at a science museum. The line plot shows the length of the insects to the nearest 1/8 inch. What is the distribution of the length of the insects? So here it says most of the data points are between 3/4 and 1. So the insect lengths are clustered between 3/4 and 1. So Ms. Petty is underlining what the question is that they're asking. What is the distribution of the lengths of the insects?
We always underline our keywords in our question.
Ms. Petty, repeat that again. I didn't hear you.
I said we always want to underline our keywords and our questions. For statistics, we really just need to underline the question unless we had some data that was given to us in it.
Right.
This one doesn't have much data because we're looking at it.
So therefore, you will underline the question. What is it? What is the question asking us to do? So when we go down to question number 1, it says the longest insects is how many times as long as the shortest insect. Write the equation to show your solution. So if we go back to looking at the graph, we see that 1/8 is the shortest insect, and then 1 is the longest insect, 1 inch. And the cluster, the data falls between 3/4 and 1.
So look at the 1/8 and the 1. Well, it says write an equation. You can come up with a billion equations to get to this answer. But if you have 1/8 as the smallest and 1 as the largest, think about how that relates. 1/8 is just 1/8 of 1. In order to get to 1, I will have to have 8, right? So 1 is 8 times as many as 8. So you can come up with any equation you want to solve that as long as you get the answer 8 in the end. For me, my equation would be some type of visual representation, just because most of us are visual people. If I have 4, 5, 6, 7, 8, it's a little caterpillar and it has 8 little humps, and then my small baby caterpillar is only one of those. That's how I would represent it, is 1 out of 8. But the big caterpillar, which would be this whole thing, is 8 times as big as our little caterpillar, which is the one circle. Do any insects have a length that is very different from the rest of the insects? If so, what is that length?
Now, and the answer would be yes, because when you look at the graph, you have 1/8 inch. So that's different from any of the other ones, because at 1/2 you have 2, at 5/8 you have 2, at 3/4 you have 4, and so on. So 1/8 is the only one that has just 1. So your answer would be yes, 1/8 inch.
Also, what do we call 1/8 when we look at the distribution of the graph? You see how most of the data points are clustered around certain X values, and then you have a data point that's all the way out there by itself. So what would we call that?
I would call it an outlier. Correct. But we can also call it something else. Is it skewed to the right or is it skewed to the left?
So when we look at the graph, we have to think about where's the tail. Or if you want to think about it the opposite way, you can say where's the cluster. But when we name the skews, we're talking about the tail. And the tail on this graph just happens to be over here, right? So that's on the left.
So then that's another way of getting your answer. So question number 3, we're going to do this with you, and then the remainder you're going to do by yourself, and then we'll look at look at your independent work. Question 3 says, how would the line plot change if the insect's lengths were clustered between 1/8 and 1/4? So what it's going to do is look at 1/8 and 1/4. that's where your cluster is going to be. So then it would be screwed a different way. What else could you say about it?
It will definitely, yeah, I'm agreeing with the skew. Then the way I would describe it is we have a lot of short insects now. We don't have a lot of tall insects.
Exactly. So it would just be on the other side of the line plot.
Just act like these are not over here.
Okay. And also you have that vocabulary word distribution that shows how to spread out or how clustered data values are. So this is, we're talking about the distribution.
Right. So I did a little magic to the graph. You just look at it. Now our cluster's over here. And our tail is kind of on the other side. So now we're going to go on and look at your independent practice.
So we're going to do 4 with you, and then you would do the rest by yourself. And then if you have any questions, you would email one of us to ask us to explain. So number 4 says, use the line plot for problems 4 through 8. So you see the line plot shows the amount of time it took some runners to finish a charity race to the nearest 1/8 of an hour. So 4 says, so when you look at the plot, the chart, you see you have 2 hours, 2 1/8 hours, 2 1/4, 2 3/8, up on to 3. So it states, tell whether each statement about the data in the line plot is true or false. So A asks you, none of the runners finished in exactly 2.5 hours. Is that true or is that false? So what we would do is go to 2.5 hours on the chart.
Right.
When we look at 2.5 hours, there is not a point there or X saying that someone finished in that amount of time. So the answer would be true. None of the runners finished in exactly 2.5 hours.
And B, at a time of 2 hours is uncommon. So this one's a little tricky because the word uncommon. But when we look at the graph, we look at our 2 over here, and then we can just imagine all these other data points. Most of the data is clustered above the 2 3/8 all the way until 3. So yes, 2 hours is uncommon. That person would have had to run really, really fast if we're going to relate this back to a real world problem.
And uncommon just means that there's not a lot of people doing it. So there's only one person.
Right.
So that's why it's true. Okay, C. The most common time is 2 3/4 hours. So when we go to 2 3/4 hours, we see there's 1, 2, 3, 4, 5 persons who ran the race in 2 3/4 hours. So that would be true because it's common because there's a lot of people doing it.
Right. And the most people did it when we look over here too. It's the tallest one. So
exactly.
If we're going to use our words, we can know there's also a peak at 2 3/4 hours.
Exactly. So that's one of your vocabulary words as well.
So most runners finished around 2 7/8 hours. Well, we just told you what the most common time was, right? It's 2 3/4 of an hour. So when we look at 2 7/8, we can't say that most of the runners finished in because one more person, it only takes one, finished at the 2 3/4 hours and around. So
but you do have 4 runners who had finished in 2 7/8 hours.
Right. So most of the runners finished in. So this is where I have to go back and underline these keywords.
So 2 7/8 hours. So that I would say that's true because it says most runners finished in around 2 7/8 because you got 5 runners in 2 3/4, which is around 2 7/8.
Right. And also this will go back to our inequalities on the number line. So this is why I want to think long and hard about this one. I would put my circle in 2 7/8. I will close the circle. And we're not talking about did they all finish right there on the circle? We're talking about this whole part.
Exactly.
So yes, when we count those up, that's mostly everybody except 4 people.
And that's why you have to be careful with the vocabulary words.
Right. You have to look at those keywords because it says most runners finished in around, not at. All right. I would expect people to get 5, 6, and 7 on their own. Let's see.
And if you struggle with 8, don't worry about it. You can do it. Look at it, read it. If you think you're going to struggle with it, contact us.
Right.
But don't worry about it too much.
So let's look at 8. So pause the video and attempt it on your own. Attempt 5, 6, and 7 on your own. And we're going to come back and look at 8. Okay, suppose the times for additional runners were recorded, including a new slowest time and a new fastest time. What would be a set of reasonable times based on the data in the line plot? So this isn't just saying, look at what we have, it's saying add a slowest, so 10 additional runners.
Right.
Plus a slowest time and a new fastest time. And what would be a reasonable set of times? Oh, this is you to come up with some more data. So look at the line plot and we're going to add 10 new points. But because we're going to have a new slowest time and a new fastest time, we're going to need to extend our line plot first, right?
Yes, so we can add a slower time to be 1 1/2 hours.
Let's put that right there. And our new fastest time.
And the fastest time could be 3 1/2 hours?
Or 3 1/8.
3 1/8 too.
Right, that's a horrible 3. I take mark right here. So we have now, so that's 2 of our 8 points. I mean, 2 of our 10 points. We need 8 more, right? So where do you think the other points would fall just by looking at the data that we have already?
We can do 2 5/8.
Right.
And maybe 2 3/4.
I would put 2 there because we have more.
But we can add more.
Because most of like our data, if we're gonna guess about where more people finished, I still think it's gonna be in the same place, right? Because more people already finished this way.
Right. So you have to remember with this question, the answers are going to vary depending on where you put your data.
Right. You can put it wherever you want, but the skew should look the same and the cluster should look the same. Because it's the same type of people. We're going to assume it was the same type of people, right?
Exactly.
So let's put some 0.2, 3, 4.
So you got to remember, sometime in math, some of the answers are dependent on how you work out your particular problem when it gives you questions like this.
Right. So just like in our previous lesson, for a question like this, is no right or wrong answer. Like you pick whatever you want, but it should be a reasonable answer. That's all it asks you for, a reasonable set of times. So as long as your answer is reasonable, you're going to be okay.
Exactly.
All right. And that's really it for today. So as always, if you have any questions about any of these questions or anything that you're just working on, let us know and we will respond and help you out with that. And I hope you guys are staying safe while we're out here dealing with these unprecedented times.
And be nice and do everything you have to do and listen to your parents.
Right. All right. Bye, Eagles.
Bye-bye. See you later.